Hello everyone, I'm James and welcome to episode 5 of the OpenGL tutorial series. Today we're going to be adding the transformation framework and hopefully we'll get some fancy motion on our triangle at the end of the video. Let's begin!
I've created a class called transformation in a header file with the same name. There are three kinds of transformations. The first one is translation, which I'll store as a three-dimensional vector and call it position. We'll need to include GLM. The second kind of transformation is rotation, which I'll be representing with a quaternion. I won't be explaining how a quaternion works in this series. This requires us to include the quaternion header in the GTX folder. The last kind of transformation is scale, which I'll represent with a three-dimensional vector as well. I'll add a constructor that initializes the three fields. For convenience, I'll make the position default to 0, 0, 0, the rotation default to a quaternion identity, and I'll default the scale to 1, 1, 1.
A quaternion identity is a quaternion that represents a null rotation, so absolutely no rotation.
I'll add a method to rotate the transformation by a quaternion. This will set the rotation to the new rotation multiplied by the old rotation, and the result is normalized.
Combining two quaternion rotations is done with the multiply operator. Finally, we need to normalize the quaternion just like we do with vectors. Quaternions need to be normalized as well.
I want to add another method. This will convert the transformation into a 4x4 matrix. We'll first create a translation matrix from the position. To get the rotation matrix, we just need to convert the quaternion to a 4x4 matrix. Then we'll create the scale matrix. We'll finally return all these matrices multiplied together. It is important that you use this order of multiplication. Now I'll create an instance of the transformation below the mesh. We'll need to include transformation.hpp.
I changed the update code a bit so that it limits the frames and prints the frame rate. The code will be available on GitHub. Now as you can see, stdchronoTimePoint doesn't exist. This is because we're still using 2014 standard. Right here in the properties, go to general and set this to, I'm going to just set it to 20, but 17 I think should be enough. Now the errors are gone. Also, the render code is all here. We have the clear, the draw mesh, and the window.swap buffers. The update code is going to happen right here. In fact, we're processing events in this part. If we run, there you go, we get the same result. Now let us make transformations work.
To test this, I'll create a variable which I'll call x. I'll add the frame time to x after we process events. I'll set the transformation's position's x value to sine of x just to test. If we run now, nothing will happen. We need to pass the transformation to the vertex shader with a uniform.
As I briefly mentioned in the previous video, uniforms are the bridge between our C++ code and the shaders. We are going to create a transformation matrix. That is why we made that toMatrix method in the transformation. Then we'll grab that matrix and send it to the vertex shader. And the vertex shader will transform our vertices. That's why it's called a vertex shader, because it processes vertices. And that is the power of the vertex shader. Let's go ahead and implement the framework to send uniforms to the shaders.
In the shader class, I'll add another method to set a 4x4 matrix uniform. The first parameter being the uniform name and the second parameter being the value. Remember to include GLM. To send a 4x4 matrix uniform, we need to call the GL uniform matrix 4FV. The first parameter is the uniform location. This is an integer. To get this integer from the name, we need to call GL get uniform location. This takes in the program ID and the string representing the name. The next parameter is the count of matrices we want to send, in our case 1. Next is a boolean parameter, which we set to true if we want to transpose. We don't want that, so I'll pass false. The last parameter is a pointer to an array of floats that make up the matrix. We'll grab the pointer with the glm value ptr function. You'll need to import type ptr.hpp from the gtc folder, which is in the glm folder. Back in the main function, right before we render the mesh, I'll set the uniform with the value of transformation.toMatrix. All we have to do now is add the uniform in the vertex shader and multiply it by the vertex position.
Adding the uniform to the shader is very easy. All we have to do is go to here, add the uniform, mat4, and we call it uwvp. All I need to do is multiply it by the vertex position, and that should give us the transformed position. Now if we run, look at that, we have very simple but indeed motion. Awesome. I added some rotation and some scale, and now if we run, this is what we get. So rotation and scale are working. Now it's time to add the camera framework. Right now we don't have a concept of a camera. A camera has two properties. One of them is a transformation. The second one is a projection. To work out the transformation, it's very easy. If we translate the camera to the right, for example, the scene needs to be translated to the left. So translation is basically done in the opposite direction. Rotation is very similar. If you rotate clockwise the camera, the scene has to be rotated anti-clockwise. And the pivot is the camera itself. With scaling, it's not really that important, but if you scale the camera up, then the scene has to be scaled down. Now, what about projection? What we need is a perspective projection. A perspective projection basically works by making things that are far away look smaller and making things closer look bigger. GLM gives us a perspective projection out of the box, so we don't need to do any calculations ourselves. We just need to call GLM perspective and create a perspective matrix. Because all these transformations are done with matrices, and it's actually very easy. We just need to multiply them together, as you'll soon see in the code.
We'll start with an empty camera class. The first thing we'll need in the camera is a transformation, so we'll include transformation and add the field to the class. The other thing we need in the camera class is the projection. This will be represented with a 4x4 matrix. I'll create a constructor to initialize these fields. Now we'll add two helper methods, one to get the view matrix and one to get the view projection. The getViewMatrix is exactly like the toMatrix method in the transformation class. However, everything is flipped. So the position matrix is created with the negated transformation's position, the rotation matrix is created with the conjugate of the transformation's rotation, and the scale matrix is created with 1 over the transformation scale. Finally, we'll multiply the three matrices in the same way we did in the transformation class, but in reverse. GetViewProjection is very easy. All we have to do is multiply the projection with the view matrix. Back in the main file, let us create a camera. Make sure to include camera.hpp. I'll pass in a transformation 5 steps backwards in the Z direction. For the projection, I'll pass a perspective projection. The first parameter is the field of view in radians. I want the field of view to be 70 degrees, so I'll pass in 70 converted to radians. For the aspect ratio, I'll pass in the window width divided by the window height. However, I forgot to store the width and height in the window class. So in the window class, all we have to do is add one field for the width and one field for the height. In the window constructor, we'll initialize both fields to the width and height. Back in the main file, I'll pass in the window width divided by the window height. Make sure to convert one of the expressions to a float so that you won't get an integer division. For the z near, I'll hardcode 0.1 and for the z far, I'll hardcode 1000. Finally, we'll send the camera view projection multiplied with the transformations matrix as a uniform. To make the scene more fancy, I'll remove the scaling effect and make the rotation take place on the y-axis.
Now let us run and see what we have. Look at that! We finally have a 3D triangle. No more 2D, 3D. Awesome. And that, my friends, is the end of this video. In the next video, we are going to take a look at more complex meshes and discuss the topic of indices. If you want to be notified when the next video is coming out, please consider subscribing to the channel and hitting the notification bell. With that, thanks a lot for watching and goodbye.